All right, so now we are going to work with a more general version of the chain rule. So the second case is more complicated. Now, let me explain the logic behind the chain rule. So now the logic behind the chain rule is based on matrix multiplication, right? So if you are familiar with matrix multiplication, then probably it'll make sense to you. So if you are not familiar with matrix multiplication, you can just skip this, I don't know, a few minutes of these explanations and just try to memorize all the different versions of the chain rule. But hopefully, um, matrix multiplication should be more or less familiar, and I hope that my explanations are going to make sense to you. Now, okay, so let me explain what I mean. So suppose that we have like a chain of functions. So we have let me draw it like this. So let me suppose that there is R2 with coordinates S and T, and then we have R3 with coordinates X, Y, and Z, where X, Y, and Z are functions of S and T. And then we have R1 with coordinate W, where W is a function of X, Y, and Z, right? So we have a composite function, essentially. Now, X, Y, and Z are functions of S and T, so which means that we can compute partial derivatives of X, Y, and Z with respect to S and T. So therefore, we're going to have 6 different partial derivatives that we can write as a matrix. So rows of this matrix correspond to dependent variables, X, Y, and Z, and columns correspond to independent variables. So that there's going to be a matrix of partial derivatives as T. Sorry, yeah, but by the way, I'm going to use this example with two variables mapped to three variables and then mapped to one variable. But in the subsequent lecture, we're going to begin with 2 to 1, but then we're going to develop this into other cases. I just think that it is a bit easier to work with 2 and 3 because then some matrix multiplications are going to make sense, while the reverse order is not going to make sense. So it's just kind of easier. Anyway, so here is what we do is so there is a matrix of partial derivatives of x with respect to s and t. Y we can differentiate with respect to s and with respect to t, and z we can differentiate with respect to s and with respect to t. Right. So here we have a 3 by 2 matrix of partial derivatives. Right. So 3 by 2 because the target space is R3. So there is x, y, and z. And here we have a matrix of partial derivatives, well, just 1 by 3. So W with respect to x, Wy, and Wz. So all these are partial derivatives. Okay, so this is a matrix is 3 by 2, and this is a matrix 1 by 3. All right, so at the same time, if we, if we have some expression for W in terms of x, y, and z, and x, y, and z are in turn some expressions in s and y, then we can substitute um, expressions for s and t into x, y, and z, and then W is going to be a function of s and t, right? So we have a composite function from R2 to R1. So here we have the variables s and t, and here we have the variable W. Right? And here we are going to have a matrix of partial derivatives with respect to s and with respect to t. Right? So this is a 1 by 2 matrix. Now, if you have a 3 by 2 matrix and a 1 by 3 matrix, how can you make a 1 by 2 matrix? So you've got to multiply them in this order. So first 1 by 3 matrix. So you can take a 1 by 3 matrix, multiply with a 3 by 2 matrix, and then you will get a 1 by 2 matrix, right? So what it means is that if we take the matrix Wx, Wy, Wz, so this is 1 by 3, multiply by the matrix Xs, Xt, Ys, Yt, and Zs, zt. Then we will get our matrix um, ws wt, right? So this is 1 by 2, and this is 3 by 2. Well, in particular, it means, well, element by element, it means the following things. So it means that, so if we look at this element, right? So this element of the target matrix is the product of the first row of the first matrix and the first column of the first matrix. So it means that ws is wx xs plus wy ys plus wz zs. Okay. And now let's look at the second one. Let's say, I don't know. So this element, so it's going to be the product of the first row here and the first column here, right? So in other words, it means that wt is going to be wx times xt plus, well, wy times yt plus wz times zt, right? So basically the reason for the chain rule is that the chain rule appears out of matrix multiplication of matrices of partial derivatives. Okay, now I hope it makes sense to you. So again, so if it doesn't make sense, if then just forget about it and just try to memorize different versions of the chain rule. But if it does make sense to you, then you will probably appreciate the fact that so all the versions of the chain rule are just kind of matrix multiplication. So they are all explained by multiplication of matrices of partial derivatives. And the real life application of this is artificial intelligence, right? So artificial intelligence is mostly based on deep learning. So on deep learning models, and in order to train a deep learning model, what they do, so they have these artificial neural networks, and there is a kind of a lot of layers in artificial neural network, and that they compute partial derivatives with respect to all the parameters. And in order to pass from layer to layer, one needs some uh, kind of to apply this chain rule. And since the chain rule is the matrix multiplication, so because of that, um, computers are able to train deep learning models fairly efficiently because we have special devices like GPU and TPU are special devices to perform matrix multiplication very efficiently. So, and deep learning models are, well, training deep learning models is essentially, well, in the heart of it is essentially a clever application of this chain rule, which in turn is the matrix product. So that's the idea. Okay. Now, again, so if it doesn't really make sense to you, then just don't worry about it too much. So then you can just memorize different versions of the chain rule. That there is a certain pattern. It's not like that. It's completely out of the blue. So there are some patterns. Okay. So here is the kind of chain rule for the situation where z is a function of x and y, where x is in turn a function of s and t, and y is a function of s and t, right? So in terms of what I just explained, so we have R2 with st, so then there is R2 with xy, so and x and y are functions of s and t, and then there is r with r1 with the variable z, and z is a function of x and y. So that's kind of, and whatever is written here is just the matrix product of matrices of partial derivatives. It's just that in this case is 2 by 2 um, and 1 by 2. Okay, so here is how we can apply it, right? So let me show you how we can do it. So in order to actually do it, so we need to compute all the partial derivatives, but here they're fairly simple. So let me just write a chain rule. So the derivative of z with respect to s is the derivative of z with respect to x times the derivative of x with respect to s plus the derivative of z with respect to y times the derivative of y with respect to s. All right. So now the derivative of z with respect to to x, right? So I'm going to look at this expression and differentiate it with respect to x. All right, so it is going to be just e to the x times sine y. So now I'm going to differentiate it with respect to y, right? So yeah, times xs, sorry, times xs. So now I'm looking at this expression and I'm differentiating it with respect to s. So the derivative of x with respect to s is t squared times t squared. So plus the derivative of z with respect to y, right? So the derivative of z with respect to y, again, I'm looking at this expression and I'm differentiating it with respect to y. So it's going to be e to the x times cosine y. And now I'm going to look at the derivative of y with respect to s, this expression with respect to s times 2st. Okay. Well, now I can substitute, you know, this is a mixed expression. It has both x, y, and ts. So I can now substitute for x and y. I can substitute their expressions in s and t, right? So e to the x is really e to the s t squared times sine of y, which is s squared t, times t squared plus e to the x. Well, x is s t squared times cosine of y, and y is s squared t times 2st. Right, so this is the answer for the derivative of z with respect to s. Okay, so now I'm going to compute the derivative of z with respect to t. Well, and again, so according to the chain rule, it's going to be the derivative of z with respect to x times the derivative of x with respect to t plus the derivative of z with respect to y times the derivative of y with respect to t equals now. So where can I find z, the derivative of z with respect to s? So note that it's actually this expression, right? So this is in fact zx. So I can just copy it. So e to the s t squared times sine of s squared t times xt. So to find xt, I'm going to look at x and differentiate it with respect to t now. So it's going to be to 2st plus. Okay, so now I have zy here, and where is zy? It is this expression, right? So this is the derivative of z with respect to y. So I can just copy it, e to the st squared times cosine of s squared t times, well, and now I have the derivative of y with respect to t. So it is this expression, and I'm going to differentiate with respect to t, and the derivative is s squared. Okay, so this is how we can apply the chain rule to a function of two variables. Well, two variables that in turn depend on two other variables. Okay, so here is the ds. So this is again all the information, just so that it's easier for you to make sense out of lecture notes later. And here is the second expression. Okay. All right. So next example. So the chain rule. So here the chain rule is kind of a little bit different. So now we have w is a function of x and y, right? And these x and y are in turn functions of three variables, right? So basically what we have here schematically is we have three variables, s, t, y, right? So then we have a map from three variables to two variables, x and y. So this means that x and y are functions of s, t, and u. And to R1 um, with the variable w, which means that w is a function of x and y, right? And again, so if you remember the logic with the matrix multiplication, and you can probably work it out yourselves. And in fact, it is a good exercise to pause the lecture and to try to work it out yourselves. Um, Otherwise, you can just just look at me doing it. So now w is in the end is a function of three variables. So we are going to have three partial derivatives. So the partial derivative of w with respect to s is going to be w x x s plus w y y s. Sorry, this is y s. So the partial derivative of w with respect to t is going to be wx x t times w y times y t, and the partial derivative of w with respect to uh, u is going to be w x x u plus w y y u. So all these are partial derivatives. So it is a little bit kind of boring, but yeah, that's the chain rule. Well, for different kind of situation of chain rule, right? So this is the same thing printed out, and so let me work it out. Some specific example. Um, so that's yet another version. So I will not bore you with details again. So let me just um, mention that here we begin with R2 with variables s and t. So then x, y, and z are functions of s and t, R3, x, y, z, and they map to R1 with the variable w. So this is exactly the explanation that the example that I started with, that I began with in the first place. Okay, so here is the resulting expressions, and there is one last example of an application of all this stuff, right? So let me show you how we can apply this stuff on fairly complicated in a fairly complicated situation, right? So here, so notice that here u is a function of three variables, right? So we kind of have this situation. So the three variables x, y, z are mapped to one variable, and then in turn these variables are functions of s and t, right? So we have R2 with variables s and t. Okay, so how we are going to do this? So let me begin with some probably just in order to simplify things. Let me use this information, so this numeric information um, to figure something out, right? So if r is 2, s is 1, t is 0, let me compute x, y, and z, right? So x is going to be, well, is rs e to the t, so r is 2, s is 1, e to the t is 0, so x is 2. So y is rs squared, so we have 2, then 1, s is 1, so 1 squared, times e to the minus 0, so which is 2. And z um, is what is r squared, so is 2 squared times 1 times sine of 0, and sine of 0 is 0, so this is just 0. All right, so we're going to apply this chain rule, you know, with having in mind that x is 2, y is 2, and z is 0. Okay, so let me just, yeah, so here is the chain rule for your information, by the way, but I'm going to just copy it now, right? So the derivative of u with respect to s is the derivative of u with respect to x times xs plus uy times ys plus uz times zs, right? So this is the chain rule for our situation. So and now we've got to just compute all the ingredients that we have here, and don't forget that we also have some useful information. So we know that r is 2, s is 1, t is 0, and I've just computed that x is 2. This was given initially, and x equals 2, we computed it. So y is 2 and z is 0. So this we just computed. All right. So now let me apply the chain rule. So in order to apply the chain rule, I've got to compute expressions for all the partial derivatives that appear in the chain rule. So first ux. So ux is, to find ux, I need to take this expression for u and differentiate it with respect to x, right? So it's going to be 3x cubed y plus, well, the second term is 0. So, okay, now what is u? I'm going to need uy. Wait, uh, it is more convenient to just immediately substitute the given values. So 2, 2, and 0, right? So for the specific values of r, s, and t, we're going to have 3 times x is 2 times 2 cubed times y, and y is 2, right? No, stop. It's not 3. Yeah? Sorry, it's silly. So it should be 4x cubed. 4x cubed, of course. So it's 4x cubed y. Um, 4 times 2 cubed times 2. Well, and this is, I believe, 64, right? Yeah, 64. All right, so this is ux. Now uy. Um, Let me derive uy. So the derivative of u with respect to y is, now what I've got to do, I've got to take the same expression and differentiate it with respect to y now. So x to the 4y, the derivative is x to the 4 plus y squared z cubed. Z cubed is now constant, so it's 2y z cubed. So now let me substitute the specific values that we have. X is 2, so we have 2 to the 4 plus 2 times y is 2, and z is 0, so 0 cubed, so which is 16. Okay, and u z. So what is the derivative of u with respect to z? Basically, we are still looking at the same expression for u. Now we are differentiating it with respect to z, and with respect to z is going to be, so yeah, so it's going to be just 3y squared z squared, and z is 0, so for the specific values it's going to be just 0. Okay, so it wasn't too hard, hopefully. So let me just change color to use a different color to find derivatives with respect to s, right? So the next thing is that we've got to differentiate with respect to s. So, and we've got to differentiate 3 different expressions, right? The derivative of x with respect to s is going to be r e to the t. So now we are looking at these values. So for the specific values, 2, 1, and 0, we have e to the 0 is, let's just write it 2 times e to the 0, just 2. All right, now uh, this was x to xs, now ys. So the derivative of y with respect to s is going to be, um, now I'm looking at this expression, it's going to be 2rs to the minus t, with the specific values is 2 times 2 times 1 times 0 times 1 is 4, I believe. Um, yeah, it's 4. And now the derivative of z with respect to s, now we're looking at this expression, is going to be r square sine t, and t is 0, so sine of 0 is 0, so this is going to be 0. So it is somewhat simple. Okay, good, good. So now let me, I don't know, change the color one more time. Okay, so now I'm going to use this expression to get the final answer. So us is ux. So ux is 64. So it's going to be 64 times xs. Xs is 2 times 2, plus uy. Where is uy? So uy is 16 times ys, 4, plus uz is, where is uz? Is 0, is 0 times 0. And this is, I believe, 192. Okay, so this is how we can apply the chain rule in this situation. And did the same thing for you printed out, and this is the final answer. Well, I'm sorry it was a little bit long and boring, but well, that's life. Okay, so the chain rule is over. So please do this little quiz, and there is just one last part in this lecture remaining.